So, the aim of this video is to give you practice integrating the function cos to the power of 5. And the key point to notice is that this is an odd power and it's a definite integral, so you should also think about the sign of the result that you obtain. So have a go at it with pen and paper. Detailed solutions and some comments follow. And if you come back when you've had a go at it, we can discuss the answer. Okay, welcome back. Let's go to the next slide. So this is the integral that we want to find, and the key point to notice is that the cosine here is raised to the power of 5, and that tells us not to use the double angle formula. So, for example, double angle formula allows us to rewrite cos squared theta as a half 1 plus cos of 2 theta. So you might think I could use this in here, but that would mean that cos of theta to the power of 5 would be this, which is this, raised to the power of 5 halves. So because this is an odd power, we'd have a half power here, a fractional power. And that tells us that really we can't use this. It's going to lead to an integral which is difficult to calculate. So the moral is we use the double angle formula for even powers, and for odd powers we have to do something different. So what we do is we strip off 1 power of the cosine here. So we have the cosine multiplied by an even power of the cosine. And we still do not use this formula here. Instead, what we do is we say, well, this is cos squared theta all squared, and then we can rewrite this as 1 minus sine squared from our standard result that cos squared plus sine squared is 1. And then because this is all squared, we expand it and we find that cos to the 5th of theta is cos theta multiplied by what we get when we expand this. So it's 1 minus 2 sine squared theta from the cross terms, plus when we square this, sine to the 4th of theta. So now we've gone from having one integral to having 1, 2, 3 integrals. But the good news is that each one of these 3 integrals is actually easy. So let's just write them out on the next line. We'll go back to the variable x. So we have the integral from pi over 2 to pi of cos to the 5th of x with respect to x. And that's equal to the integral from pi over 2 to pi of cos theta times 1 is cos theta minus 2, and then it's cos theta times sine squared theta plus cos of x times sine to the 4th of x. That's a standard integral, and here we notice that this is the derivative of sine of x. And in the same way here, this is the derivative of sine of x. So we can hope to do these integrations by inspection. So let's just think about what we would do. Well, the integral of cos x is sine x. If you differentiate sine, you get cos. What about this one? Well, we add 1 to the power, so sine squared goes to sine cubed. And were we to differentiate that, we would pull a 3 in front, reduce the power by 1, that gives us the sine squared, and then we would multiply by the derivative of the function that was being cubed. And the function that's being cubed is sine x, so we'd multiply by the derivative of sine x, which is cosine of x. So if we differentiate this, we would get plus 3 cos of x sine squared x. We want a minus sign, so that's easy. We'll just put a minus sign there. And then we'll put a factor of 1 over 3 that mops up this 3 when we bring it in front through differentiation. But we also need this 2, so let's just put a factor of 2 there. And similarly here, well, here it's going to be plus when we differentiate it, and that's good. We get a factor of 5 sine to the 4th of x multiplied by the derivative of the function that's here to the 5th power, sine, and the derivative sign is cos. So if we differentiate this, we would get 5 cos x sine to the 4th x. So that's easy to fix. We just put plus 1 over 5 in front. And now we've carried out each one of these 3 integrals. At the top, the upper limit, we're going to get sine of pi here, here, and here. Sine of pi is 0. So all of this vanishes at the upper limit. So we'll put 0 minus, and then we'll open a big bracket and evaluate this at the lower limit. The sine of pi over 2 is 1, so we're going to get 1 minus 2/3 times 1 cubed, so that's just minus 2/3, plus 1/5 times 1 to the 5th, that's just plus 1/5. So now we want to work out what that is. And 1 minus 2/3 is 1/3. So we have a third plus a fifth. The common denominator is 15. And a third is 5/15, and a fifth is 3/15. Adding the two of them together means the argument of this bracket is 8/15. And outside there is a minus sign. So we should have obtained minus 8/15. And that is our answer for this definite integral. On the next slide, I'm going to talk about its interpretation and the sign of our answer. So what I've drawn here is the function y is cos of x, and then our integrand is cos to the 5th of x. So I've just tried to draw what cos to the 5th of x looks like roughly. The cosine is between plus and minus 1, and therefore when you raise it to a larger power, it is going to become, its value, its modulus is going to become smaller than that of the cosine. So it's going to lie between the cosine curve and the x-axis, and it just touches it at x is when the function vanishes, when the cosine vanishes, when the cosine is 1, and when the cosine is minus 1. So this is the graph of cosine to the 5th over our range of integration. And this area between the curve and the x-axis is going to be the value of the integral up to a minus sign. Because this curve lies below the x-axis, the value of the integral is minus this area. So we expect our integral to be negative. And the answer that we obtained was minus 8/15, and so that's completely correct. I've also drawn on this graph a little rectangle. Our integral that I'm calling here I is negative because the integrand lies below the x-axis, but it is going to be bounded between 0 and minus the area of this rectangle. This rectangle has height 1 and base pi over 2, so its area is pi over 2 times 1, that's pi over 2. And because it lies below the x-axis, its contribution to the integral will be minus its area. So therefore what we're saying is that our integral is going to be bounded between 0 and minus pi over 2. And if you think about that, that is very roughly minus 3 over 2, and that is very roughly minus a half, and minus a half does lie between 0 and minus 3 over 2. So our integral fulfills this bound. Okay, to conclude the video, I'm just going to give you 2 exercises with answers on the next slide. So here are 2 exercises for you to try if you would like to practice this. One of them is to integrate sine cubed theta. Again, you see it's an odd power here, and this is the answer that you should obtain. The other question is a definite integral, and it's an integral from 0 to pi over 2 of sine cubed theta times cos to the 5th theta. So both of these functions are raised to odd powers, and the answer you should obtain is 1 over 24. Now, if you pause now, you can calculate both of these. If you need a hint for this integral, I will give you a hint in a moment. Okay, here's a hint for you about how to perform the second integral. So what you could do is you could write sine cubed theta times cos to the 5th theta as sine cubed theta cos to the 4th theta cos theta. So in other words, what we've done is I've stripped off one of the powers of cosine, and then this could be written as 1 minus sine squared all squared. And that would then generate sine cubed theta by 1 minus sine squared theta all squared times the cosine of theta. And you could expand this, you would get 3 integrals, all of which you can perform by inspection. But this is too hard. More easily, what you can do is the following. So, more easily, what we'll do is we'll say, well, both of these powers are odd. So in both cases, we could do something like this of pulling off one power, but this is a larger power, and when we've pulled off the one cosine, we're left with a larger even power to expand. So here, why don't we look at the smaller odd power? So I'm going to write it as here, sine of theta times sine squared theta times cos to the 5th of theta. So that's sine theta, open brackets, and now the sine squared is 1 minus cos squared theta, all multiplied by cos to the 5th of theta. And you see that this way we get 2 integrals. We're going to get the integral of sine theta times cos to the 5th theta minus the integral of sine theta times cos to the 7th theta. So that's 2 integrals that we can perform by inspection. So if you're faced with something like this and both powers are odd, choose the smaller power to pull off one of the factors. With that, I'll stop this video.